Um, Hello. So I guess today I'm going to be talking about NLP, which stands for Natural Language Processing. So yeah, thank you, Sam and Vaki, for organizing. So what is natural language processing? I assume you all know what the word natural means and the word language means and the word processing means. So you just put them together and it's about the processing of natural languages. So basically it's somewhere in the intersection of machine learning, data science, and linguistics. In other words, how do you get your computer or some machine to understand a human language? Yeah, so today I'm going to just describe some of the topics of interest in NLP. I should say from the start, I'm not a NLP professional. It's just kind of some things I've been reading about, but hopefully it will at least get you interested in it, and then you can go read actual references from there. So why is natural language processing important? What can you do with it? Well, it turns out it's super practical. So for instance, maybe you're in a foreign country and you don't speak the language. So maybe you're in Spain and you need to translate "Hi, how are you?" to, "Hola, ¿cómo estás?" And right, this is fine. If you have an English to Spanish dictionary, you can do each word individually, but you also need to understand kind of the syntax, how you kind of paste those words together to form sentences. And so this is where something like a Google Translate would be helpful. There's also this thing called named entity recognition. So this is maybe if you're in media or you run the media for some company and you want to figure out where your company has appeared in the news. So named entity recognition, the idea is to parse a news article or a Wikipedia entry or anything like that and pick out the named entities. So you would want to label the words or the chunks in this sentence. For instance, Matt Damon is a person. Ben Affleck is a person. Boston is a city. And Asta is, well, as you can guess, a restaurant in the city. So this would be like a place of interest. Right, so if you can paste all of these things together, for instance, maybe you would say that, oh, Matt Damon and Ben Affleck are working on a movie together or something. There are many applications you can imagine. Another thing that kind of goes along with named entity recognition is sentiment analysis. So one thing a lot of companies are doing now is they're parsing essentially millions and millions of tweets. And from Twitter or any kind of social media, they're figuring out what people's thoughts are on it could be a company, it could be a politician, it could be anything like that. Okay, so one thing you could do is you could say, well, here I have this database of 100,000 Twitter users. They're all in their 20s and they're all white men. And lately they have all been tweeting about Rudy Giuliani and how they think he's pretty stupid. And then you can kind of use that to guide your policy or decision-making process with 20-year-old men. So maybe you need better optics in a certain area of the country or something like this. And so with natural language processing, these are all things that can be essentially automated and just done for you once you have the proper machinery built up. As you can imagine, natural language processing is very hard. human languages have a lot of subtleties and a lot of technicalities. There's a reason why it takes humans years and years to start really speaking full sentences and then start speaking sentences which kind of make sense. So feel free to chime in. I mean, what do you think the subtleties or technicalities that make this hard in particular would be?
Well, I'm still working out how to make sentences that make sense.
Yeah.
But yeah, I think like a lot of it could be like context, right? Certain words and like, yeah.
For one, like you don't have a particular fixed input size, right? Like you would have in a table or a list. Like sentences can run on.
Yeah, so context is a big one. You have a ton of words which mean different things depending on what context you're in, and it's not necessarily easy to distinguish. So if you're just talking about, say, red, the color red, well, one, that could just be describing a color. It could also be describing like a human emotion. So you could be saying, oh, he's red in the face or he's angry. It could also be used to describe undercooked food. There are even words which the same word, so these are called autoantonyms. Not only do they mean different things in different contexts, but they're antonyms in different contexts. So the word clip can mean to clip two things together, but it also can mean to clip something with scissors. In other words, to cut it apart. The word buckle can mean kind of to strap into something, or it can mean kind of to fall apart, like he buckled at the knees. So how do you distinguish when I'm using that form of buckle versus the other form of buckle? The input size, as Vasu was saying, this also can make it technically difficult in terms of if you're running some classifier algorithm, like what do you put into your function if the size of the sentence is varying? We'll actually see a little bit of that later on. Some other things obviously would be like regional dialects. So for instance, if you're in the northern United States, the word Coke means a very specific type of soda. If you are in the South, the word Coke could refer to soda more generally. And also language changes over time. So in the past 4 years, for instance, the word news or media probably has a more negative connotation than it did in the early 2000s, because, right, that fake news and fake media has kind of been taking the United States by storm, and that tends to change the way we think about words.
Yeah, Tom, I was thinking about this too, like, especially for sentiment analysis, I would imagine that it's very subjective. Mm-hmm. And so it's very hard to like, actually interpret somebody's writing or whatever in a consistent way. Right. I mean, you have to introduce some kind of interpretive framework or bias, essentially.
Right.
Like, I actually have a nice example. So we got a whole bunch of campaign ads mailed to our house, and some of them would say like, "Oh, Kristen Gaspar stands with Trump," right? So if you like Trump, that's a good thing. If you don't like Trump, that's a bad thing.
Exactly.
Right? So it's
So this is, again, kind of ties back into context and your own personal views as well. Going back to Twitter as well, I mean, how do you deal with things like typos or slang? I mean, how many people write with perfect grammar on social media? So this is a field that's rife with kind of noise and problems. And so, of course, it's not a perfect science, and it's continuing to develop. And I'm just going to kind of introduce some ideas today. So one of the core topics in natural language processing is this concept of a word embedding. So what is it? All it is it's a map from L. So this is going to be a fixed language of words. And I don't necessarily even mean like the English language. I just mean the set of words that you care about. So for instance, this could be like even to an acronym like the FBI or something like that. Just chunks of letters which you're going to regard as a word. And you're going to map them into some big vector space, right? Because mathematically, what is a string of letters? We don't really know how to turn that into a function or use that with a function. But if we map it into a Euclidean space, well, we can do things like measure similarities and things like this. What do we want out of a good word embedding? Well, for one, similar words go to similar vectors. Similar, of course, is in quotation marks because I'm not going to tell you what that really means, but it should mean something like a synonym, like good and great, should go to similar vectors in some measure of vector similarity. So that's usually known as cosine similarity, if you know what that means, but it's not that important. Just as important, dissimilar words should go to dissimilar vectors. So if I have good and bad, those should be very far apart in my vector space. Finally, one very important thing is, I haven't told you what n is. So n should be within the realm of being computable. In practice, what that means is you don't want n to be much larger than 100 or maybe 1,000. I mean, there's no hard bounds, but when you're doing machine learning and natural language processing, you're doing a lot of linear algebra. And if your vectors are size 200,000, well, then you're going to have matrices of size 200,000 squared floating around, and there's no hope that you're going to do anything useful with it. So the main thing I'm going to talk about today is give you an example of good word embeddings and see what you can do with it, because I think it's really cool. Before I do that, I should give you a bad example of a word embedding. So for instance, this is known as the onehot embedding. The reason it's called onehot is that there is one non-zero entry and everything else is zero. And all you do is you take every word that you're interested in. So you could order them, say, alphabetically. I don't know if this is actually the alphabetical ordering of the English language, but I feel like it's fairly close. And you just map it to, well, this is the first word. So the first entry is 1 and everything else is 0. So this zy is probably close to the last word. I'm going to pretend it's the last word. So 1 goes in the last entry and everything else is 0. And everything else just, has 1 in the ith entry and a bunch of other zeros. So this lies in the dimension is the size of your language. And if a rough estimate on, say, the English language is at least on the order of 100,000. So if you look at a dictionary, it's about 300,000 words. And then if you do things like include names and acronyms and things like that, it could easily get to 1 million. So the first reason why this is bad is that these vectors are living in 100,000 dimensional vector space. And so you're not going to be able to do any computation with those. The second reason why this is bad is that these vectors are not similar in any sense of the word. So usually there's this notion of cosine similarity, which is related to the dot product of two vectors. And there's some normalization and some other terms in there, but it's related to the dot product of those two vectors. That's normally how we measure similarity in a Euclidean space. And every vector in this embedding is orthogonal to every other vector. So the similarity of everything here is 0. So how can you compare synonyms versus antonyms when they all have the same dot product? So this is an example of a word embedding, but it's not one that you would ever use in practice. So how do you get to better word embeddings? The idea here, it's kind of the idea behind modern machine learning, is that you don't teach your computer hard and fast rules. In other words, you don't say explicitly what the word embeddings are. You teach the computer how to learn the rules, and then just give it data, and it creates the word embeddings itself. So we can do this with co-occurrence matrices. So T is going to be a huge set of text. So an example of this would be like you can literally go to Wikipedia and download the text of every article they have. So you could download the text of Wikipedia and input that into your computer. And you can have your computer read that 5 words at a time. Excuse me. So this is the first line of the Wikipedia page for the word apple. So somewhere in your learning process, you would read this page, and you would read it 5 words at a time, in the sense that you would only ever look at this window of words. So an apple is an edible, and that's all you know. So you're going to do something with that window, and then you're going to shift it 1 word to the right. So the next window would be apple is an edible fruit. For each window, you look at the words that are co-occurring in that window. So here, apple and edible is co-occurring in the window. And you essentially turn that into a symmetric matrix. It's not exactly this, but it's close enough. It's essentially, you count the number of times that word I and word J appear in the same window. Right? The reason being, if apple keeps appearing next to edible, well, that probably means an apple is something you can eat. So you form this co-occurrence matrix S, and that gives you some kind of similarity relationships between your words. But right, this is size of your language by size of your language, so you're not done yet. So what you do is you do some sort of singular value decomposition, which is truncated. So what that means, I don't know people's background. It's essentially a principal component analysis if you are like statistically minded. Another way to think about it is you look at the k largest singular values, which are closely related to the k largest eigenvalues, and those k largest components essentially tell you the most relevant data of the matrix if I only was allowed to look at k dimensions at a time. Essentially, it's a way of reducing this matrix from L by L to, now I have, every word here, but I'm only having k entries next to it instead of the size of the language entries. Yeah, so again, you can think of this as the best projection of the vectors as a whole into a k-dimensional space. So this is a simple way of doing a word embedding, which turns out to be okay. So it's certainly better than the onehot embedding. You go into k dimensions instead of L, so you could choose k to be, say, 100, and you get very computable vectors. And kind of the point of this is you didn't hard code anything. You just let the computer look at what humans naturally do. So you fed it naturally occurring text and let the computer derive its own conclusions and its own similarities. So are there any questions up to now?
Yep. So if you're using a really crazy data set where Apple could appear next to the word zygote within like 3 sentences, then the first eigenvalue of your graph would probably be really small. So I was wondering like, sorry, of this matrix. So I was wondering if these eigenvalues actually determine whether how good something is as a training set.
Yeah, I don't know. So the training set you use definitely does matter a lot on the quality of the model you get. So if you like just used a bunch of text from 4chan, you'd probably get something pretty crazy. I don't know if you can measure that related to like the eigenvalues. I mean, I imagine you would get a good model, it would just be good in the context of wherever you got the text from. So normally what you do is you use something which is very like objectively written, like Wikipedia. It's supposed to be an encyclopedia. Or what people will do is they'll take like all of the news articles from Reuters or the New York Times over the past 20 years. But I'll talk a little bit more on that at the end.
I had a related question. And that is the following. There are some words which don't really mean much on their own. So for instance, I mean, and once you sort of do the singular value decomposition, won't these words be sort of disproportionately represented in your matrix then?
Yeah, so that's a good question. He's talking about words like the, a, and is, which appear a lot. And so maybe they're going to introduce some, not necessarily noise, but they're going to outweigh everything else. And so, yeah, in practice, what a lot of times people will do is they'll reweight some of the vectors intelligently to account for this.
Just a funny thought, maybe we could actually rank people's public speaking ability by creating their word matrices for larger and larger paragraphs they say, and calculate that first eigenvalue of this matrix. That's
okay, so now I want to talk a little bit about kind of, in some sense, what's the state of the art for word embeddings. And this is called word tovec. And specifically, I'll talk about the continuous bag of words model. So this came out of Google's research team in, I think, 2010 or sometime around that. There's a guy called Thomas Miklov. And in some sense, I mean, since this has been published, of course, there are ways to make it even better, but this is roughly, I think, the state of the art. And the idea here is that, the punchline of this is kind of the old saying that if you tell me you're friends, I'll tell you who you are. In other words, if you are friends with a lot of religious people, you're probably fairly religious because you know them for church or something. If you're friends with a lot of mathematicians, you're probably a mathematician. And so the idea with word tovec is that words which are used in similar contexts are probably similar words. So what's an example of this? So let's say again that I'm looking at the word apple. And the idea with word tovec is, again, we're going to look at a lot of text in 5-word chunks, but we're going to delete the middle word. And we're going to play the game where, based solely on the first 2 and last 2 words, we try and guess the middle word. Right, so you can see that you get quite a lot of context clues just by looking at these 4 words. So for instance, you ate something. So you know this middle word is probably some sort of food. The food is in some sort of pie. So, okay, maybe that means it's a sweet or fruity kind of object. And so maybe this is actually the word apple, right? But there's a problem because it could also be strawberry or peach or pumpkin, or it could even be like a savory pie, like a shepherd's pie or a meat pie or something like that. So these 4 words, they haven't restricted the middle word uniquely, but they've restricted it to the class of words which are edible and are eaten in a pie. So they've kind of grouped those words together in some sense. So how does this work in practice? Well, you initialize the words to word vectors completely randomly. And I've said R50. In practice, it usually goes R30 up to R100. You don't get much more after 100 dimensions. And then what you're going to do is, again, you're going to read through your text. So you're going to read through Wikipedia 5 words at a time. And you're going to have what's called this kind of softmax rule. In other words, you're going to tell the computer, given these 4 words, W3 is going to be selected to maximize something called a softmax. So a softmax, what this roughly is you're going to take the exponential of V, dot it with, say, W1, sum it up over all of the words, and then you just normalize this to get a probability distribution. So what you're doing is essentially you're picking out the word which is simultaneously most close to the 4 words in that window in some sense. And you're doing it with this, what's known as softmax distribution. So, I mean, you can argue why that distribution over something else that seems like black magic. I can't justify it for you a priori, but I can give you some pretty convincing results in just a second. So then what you're going to do...
Tom?
Yeah.
Is there maybe a physicsy explanation that has to do with statistical mechanics for why this is good?
I don't know if there's a physicsy explanation. I mean, softmax just appears a lot when you have a bunch of data and you want to turn it into a probability distribution.
Gotcha.
And so, you know, the similarity, certainly the dot product is measuring some sort of similarity between the vectors. The reason the exponential appears is that it kind of gives more weight to the really similar ones.
Okay.
Right, because it's whatever you want to call it, second derivative positive.
Yeah.
If you're much more similar, that's going to weight you much more heavily. Cool. But simultaneously, you still have like a small probability of being a different word.
Yeah. Are these complex or just real exponentials?
Well, everything is in
It's
R.
Oh.
So the dot product, everything's real. Yeah. Okay, so this is our rule. And then essentially what we do is we read through our text 1 window at a time. And depending on how you like to think of it, you're either maximizing the probability of what you've seen so far. So you're or in practice, you're essentially minimizing a loss function, or you do some sort of reversible thing where you turn a maximization problem into a minimization problem. But right, what I'm hinting at is that you're doing like a gradient descent. So what you're doing is you're looking at the text and you're saying in the first 5 lines, I guessed the word. So maybe you're looking at this line, I ate something pie yesterday, and maybe you guessed the word green or something like that. That's just from the random initialization, it said the word green should fit in there. Well, that was wrong. So obviously you need to modify your vectors somehow. And the way you do that is by computing some sort of gradient of a loss function and shifting the vectors around that you saw. So essentially you should push green kind of away from 8 pi yesterday, and you should try and push apple closer to those words. And the way you do that is by computing some sort of gradient. In practice, I mean, this is kind of the idea with a linear regression too, right? What are you doing with a linear regression? You're choosing some weights to minimize a least squared error. The difference between linear regression is that you have a small data set and you can just compute those weights. Like there's a closed form for what those weights should be. But here, Wikipedia has millions and millions of words. So you're never going to do a closed form calculation with that. So you really have to do like some sort of gradient descent to just approximate what the best weights should be. And that's really kind of it. So you take your computer, you let it read for hours and hours and hours on this text, and out it pops a bunch of, well, a dictionary of words and their corresponding vectors. So I think the next thing that I wanted to do is to show you that this isn't all nonsense and that you can actually do some pretty interesting things with this. So this was a very brief introduction to the theory behind it, and now I'll actually show you some stuff, but are there any questions at this point?
Can you say again why the computer knows that like green that does not fit in W3?
Well, you have every vector has its random word vector kind of initialized. And so you can compute this softmax function based on those vectors that you have, and you can choose the one which maximizes it based on your random first guess. It's just not a very good guess because your initial word vectors were completely random.
I think maybe Richard was asking how does the computer know that green is not a good guess?
Yeah.
Oh, because then you actually look at what the text was and you say, oh, the answer was actually apple. It's like in linear regression, how you can make a guess without looking at what the answer should be, and then you compute the least squared errors by saying, oh, how far off was my guess from the actual answer.
I see. So for each combination of like W1, W2, W4, W5, you would have to traverse the whole text, like.
No, so you read through the text window by window. At each window, you know 5 words, but you only give the computer 4 of them.
Yeah.
So the whole training is like one pass through the text, just looking at it window by window.
Okay.
Another question.
Yeah.
Roughly, how computationally expensive is this? So if you have sort of, say, the text has size n, how long will it take in terms of n to do this sort of initialization?
I don't know a good answer for that. I know it takes longer than anything that I would do on my computer, but there are like Google dedicates like days of training time for each. When they're training their machines to do this, it's not uncommon for it to take days or weeks. But
No.
I don't have like
So
a good.
for what I'm,
Huh?
So what I'm wondering about is that, say I double the size of my input text, will that double the amount of training time required, or will that sort of exponentially increase it?
No, it should. I mean, you're roughly doing the same updating step for each window. So I guess I haven't bothered to look at that specifically, but I imagine it's linear in the text size.
Oh, but, so the reason I'm wondering about this is that once you have more words, there are sort of more candidates of things that a particular thing can be similar to. So when you are doing this update step, you might have to sort of look at more things as your text size that you feed in increases. Or maybe I'm sort of wrong, I'm not sure.
I mean, the language of your words in principle doesn't change when you're training it, right? So you can go through the text in one pass and just make a set of every word that appears.
Oh, okay, I see. All right.
Oh, yeah, but so what if you had two different W3s in your data set that you give the computer? Like it could be both apple and banana. What would happen then? Because you'd have two different choices of W1, W2, W4, W5.
What do you mean two different W3s?
So for example, like if you had the words I ate apple pie, no, sorry, I ate apple pie today, and you also had I ate banana pie today. So then there's two actual instances of the sentence happening in the data set. So there's two actual choices of apple and banana.
Right. So that's why it's never a perfect science. So in principle, you're not going to get perfect answers. It will be weighted towards what the machine read or what the machine didn't read or what the machine read first and then what the machine read later. But at the end of the training process, it will always guess a single word. Like, yeah, so it's not going to get anything right with 100% accuracy. But the point is, you know that, so you don't try and use it specifically for that.
Right.
Okay, so let me show you some things you can do with this. So also, this is kind of a plug for Jupyter Notebook because I think it's really cool and you should all use it. So if you don't know what Jupyter Notebook is, it's like a way of doing Python and stuff. And what it lets you do is it lets you create files like this where you can play around with all of the tools that people have already built. So I don't know if you can see this, but hopefully you can now. So there's this thing called Gensin, and from Gensin, you can essentially download training data that people have already done for you. So you don't have to use your own computer to do all of these heavy, expensive calculations. They'll just give you a dictionary of a bunch of words and what the word vector they think should be. Yes, and it works with Sage Math, which is really nice. So what I've done is, I mean, this is just some import stuff and some preliminary functions. And I want to just show you some things you can do with word vectors. So let me. So word vectors here, I'm basically just loading in a dictionary and it's got 400,000 words in it. And it maps each one of those words to a vector of length 100. And it was created from a Reuters news text. So it's essentially millions of articles from Reuters over the past however many years, and they train this data. So the first thing you can do is you can look in your data and say, what is the word that is most similar to a given word? So for instance, the word banana, it thinks that coconut, mango, bananas plural are all similar. For some reason, potato is very similar also. So you can see, you know, coconut, mango, bananas, that makes a lot of sense. Potato, I'm not so sure about, but that's what the data said. So you can do this. Again, it doesn't just have like English nouns. So the name William is most similar to the name Thomas. It thinks that chemistry and mathematics are very similar to physics. And you can even do things like countries. So China, it tells you Beijing, Chinese, Taiwan, mainland, I don't know why. But here's the thing that I think when I saw it for the first time, really struck me and kind of sold me that this is something I wanted to learn more about. So it has to do with analogies. So what is an analogy? An analogy is those things you learned in like middle school where it was like A is to B as C is to D. So you would say something like, well, man is to king as woman is to queen, right? Because the female counterpart of a king will be a ruler, which is a woman, which would be a queen. If you have word vectors, you can think of that very mathematically. So what are you doing? Well, you're taking the word king, you're subtracting the male aspect of a king, and then you're adding to that the word vector of woman. So give me this word, take away the male part, and add in the female part, and what is most similar to that? So I have this analogy function here. So it says, what is the most similar word which is positive to B and C? So that would be like king would be B and C would be woman, and negative would be A. And it's just saying, do this vector operation and give me the closest thing to what the result is. So let's see. And it gives you queen. So you can do this, right, with kind of going from a place to a person from that place. So Japan is to Japanese, as Brazil is to Brazilian. Cake is to sweet, as curry is to spicy. California is liberal, whereas Texas is conservative. You can do kind of race. So Obama is to black, as Clinton would be white. And you can do even kind of nationality kind of things. So pizza is Italian, as taco is Spanish. So I think this is pretty amazing. It's not a perfect science. I mean, I have kind of cherry-picked these examples to work, although I didn't have to look very hard. I mean, if anyone wants to like give me an analogy that should work so that it doesn't look like I'm just lying to you, feel free to chime in.
But you say math is to math as physics is to...
How about a real analogy? Yeah.
It's stupid, but could you do A is to B as C is to D?
We can try. I don't know that these will be considered words.
Right, yeah, I mean, yeah, you might get it. Okay. Just as I thought it would
So
be.
you get something, but I don't know, maybe we can do capitals. So Paris, I haven't done this before. So Paris is to France, as Rome is to Italy.
So what does the positive thing mean?
Positive means you are similar to it. Negative means you are not similar to it. So essentially, take away the Parisian part of France and then apply Rome to it. I mean, it's not an exact science, but that's roughly what the computer is doing.
Wait, can you try salt is to pepper as ketchup is to...
They're just two spices trying to get along.
Ooh, bold, bold.
I did not see that one coming.
I was expecting mustard, but I guess that makes
Yeah.
sense. Yeah, yeah.
Yeah, so I mean, it's not perfect, but I think it's kind of cool.
That's very cool. It works very well, it seems.
Yeah, so, and you can actually, I made some plots that are going to try and exhibit this. So basically what I'm doing here is just this singular value decomposition and reducing the vectors to have 2 dimensions instead of 100, because you can plot 2 dimensions, you can't really plot 100. And I'll run all 3, but I want to do this one first. So here I have 6 words, and they're roughly like the male and female counterparts of one another, right? So boy is to girl, dad is to mom, uncle is to aunt. And if you plot this, I mean, it's not an exact science, but you can see roughly that going from female to male, you go up and to the right, right? So mom to dad is roughly like this, girl to boy is like this, aunt to uncle is roughly like that. So really what's happening in kind of the computer's head is that it's learning that up and to the right is the vector for going from the female to the male version of something. I mean, this is really loosey-goosey because I've now projected into 2 dimensions, and so take this with a huge grain of salt, but you can really see that this is the linear relationship that it's found. This one, I just did all of the states just for fun, just to see what it finds similar. So you can see Guam is on its own, which I think would make sense. Hawaii is most close to Guam. These are kind of Midwestern states, plus Georgia. Texas and California, I think it's very funny that they're so close. Again, this isn't really saying anything meaningful. I just think it's cool to look at. And another example of this is, so again, going from the land to a person from that land. So Hungary to Hungarian, you essentially go downwards. Greece to Greek, you go down right. Spain to Spanish, you go down. Asia to Asian, France to French, Britain to British. Weirdly, for America and Europe, you suddenly go up and to the right. I don't know how to explain that one, but you know, roughly what it looks like is you go down to get from the country to a person from that country. The last thing that I wanted to mention is that, as Vatsa was saying, the model you get is only as good as the data you put into it. And so you have to be really careful that you don't have kind of hidden biases in your resulting model. So what do I mean by that? Well, this is essentially the analogy code, but it just gives the top 10 most similar words instead of the most similar word. So now if we try and run this for man is to boss as woman is to what we get is words like housekeeper, lover, wife, friend, girlfriend. Whereas if we switched woman and man, what we get are actual like people in kind of leadership roles. Weirdly, we get a lot of soccer coaches.
Sam Allardyce.
But one that actually I think was pretty bad with this is with mathematics. So if I do man is to mathematics as woman is to what, it says humanities, sociology, undergraduate, right? It doesn't really think of woman as kind of in the hard sciences. Whereas if you replace that, again, it goes right back into physics, math. You can also see this here. If you do man is to math as woman is to what, it says things like kindergarten, literacy, classroom. So probably thinking of a woman as a lower level math teacher, as opposed to, if you reverse this, you get mathematics, skills, and things like that. So
That's a quick question.
yeah.
So actually the bias that stands out I mean, obviously this is biased, but the bias that stands out to me too is that it will never pick the same word again, right? Is that like coded in hard that it won't pick the same word twice? They won't say like man mathematics, woman mathematics.
I'm not 100% sure. It might be doing that, but I would have to look at it. It goes into however this most similar function works.
Okay.
Part of the way it's written might be to exclude words that you give it, but I'm not 100% sure.
Right, that seems important here.
Right, but when you swapped woman and then boss, it still gave you more authoritative roles, right? That were not boss. Like it gave you Mourinho.
Sure.
Yeah, so you can read into the specifics of this what you want, but the point is really, if you feed it, I mean, it goes back to this whole mathematics and policing argument that's been going on over the past years. If you train it on data that thinks of people in a certain way, the machine, as a result, is going to think of people in that way as well. So you do have to be a little bit careful in that aspects, but I think, you know, when you look at things like Wikipedia, it's kind of not so bad. I think that's basically all I wanted to do.
All right, let's thank the speaker, everyone. Does anyone have any additional questions for the speaker?
Yeah, I've got a question.
Oh, I had. Oh, okay, go ahead.
Oh, go ahead, Avik.
Oh, okay. So I had a very quick question. So in the plot where you showed that, so you had these countries or regions more like, so Asia, Asian, Europe, European.
Yeah.
So if you feed it into the analogy thing, so if you say, because we see a similar pattern except in two cases, right? That so if you feed it into the analogy thing, so if you say that Asia is to Asian, that America is to what, will it still give out American?
It does. So
I guess that's like
so that
it's like
could
a
be an
dimensional
artifact
thing.
of.
Yeah.
I think it's probably an artifact of your projecting down to 2 dimensions.
Okay, I see.
Yeah, but I'm not 100% sure.
So JJ, go ahead.
Yeah. So I guess what I'm wondering is if you know, like, how sort of hard-coded / like how amenable is Word2Vec to sort of being like how much does it depend on you're actually like using the English language or like using like words or letters or something? So the context being, there are these papers that what they do is they take in like whatever the equivalent of the archive is for materials science, and they dump it into this Word2Vec thing, and they look for these sort of analogies, and what they've found, like what are called like latent knowledge in literature, right? Where there's this analogy that people didn't know about, but was sort of lurking in the literature, and then they go and they do some experiments and test it. If you wanted to do that for like math, you might like, how much would you need to modify Word2Vec to deal with like mathematical notation and stuff like that?
It just depends on how good your regular expression matching is, I guess. But in general, the things you're embedding can be very general. So Word2Vec could be anything to vec, as long as you know how to kind of break up your data into chunks or into discrete objects. So I guess mathematically, if you're doing something like a text file, I mean, would you break up a fraction by its numerator and denominator separately, or would you consider that one whole thing? I don't know. That would have to be kind of a personal implementation decision.
Just to add on to this, there's a research group at Erlangen in Germany they work on mathematical knowledge representation, and they sort of deal with this sort of question that how do you sort of, represent mathematics so that you can feed it into systems like these. So if you want to check that out.
All right. Any other questions for the speaker?
Well, maybe one last one. I'm not sure if you mentioned how good is NLP in, for example, in categorizing things. So for example, you categorize adjectives and nouns or places, names, and so
on. I don't know like the best state of the art, and there's part of the problem is that there's like millions of different tests people use to see how good their machine is. And of course, people try and find the right test that makes their machine look the best. So there are things like Google has a database of analogies that you can run your word or your algorithm on and see like how well do you perform on this training set. But I don't know any like hard and fast numbers on, especially in terms of classification or anything like that.
All right, let's thank the speaker again. Thanks a lot, Tom. That was great. Thank you everyone for coming. Next week, we'll have JJ talking to us about condensed mathematics.